యూట్యూబ్ కూడా లింక్ అయి ఉంటుందా వాసు ఇది?
లేదు సార్, మనం లింక్ చేస్తున్నాం అంతే.
అదే మనం మాట్లాడేది అందరికి కనపడుతుందిగా?
అందరికి కనపడుతుంది సార్.
Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547.
నరేష్ సార్, మీరు లైవ్ ఇచ్చేస్తే నేను ప్రిన్సిపాల్ గారిని వాళ్ళందరినీ ఇన్వైట్ చేస్తాను.
వచ్చింది సార్. ఓకే,
ఈయన స్పీకర్ ఒకళ్ళు వస్తే
స్పీకర్ ని నేను చూసుకుంటాను సార్.
కరెక్ట్. ఆయన ఇప్పుడు జాయిన్ అవుతాడా అవడా? అదే
సార్ అవుతున్నారు, ట్రై చేస్తున్నా. నెట్ ప్రాబ్లం అంటే సార్ కి.
మరి క్లాస్ మొత్తం చెప్పాలి, నెట్ ప్రాబ్లం అంటే ఎలా?
అదే
సార్ కి కొంచెం నెట్ స్లోగా ఉందండి సార్. అదే కొంచెం ట్రై చేస్తున్నాను అన్నాడు.
సరే బాబు
సార్,
ఇనాగ్రేషన్ బిగిన్ చేయించు, తర్వాత జరిగిందిగా.
నరేష్ సార్ స్టార్ట్ చేయమంటారా? ఆల్రెడీ లైవ్ లో ఉందా? Good morning to all the participants who are registered for this online 5 days national level webinar. So due to COVID-19 pandemic situation, the Quiz College of Engineering and Technology, Department of Basic Science and in Chemistry Department combinedly conducting this type of faculty development training program. So thank you for all the participants who are registered for this DP, and we heartily thankful to the speakers who accepted our invitation. Today the speaker is Sarma sir. He did his Ph.D. in Banglore and he is working as a professor in GITAM University. Today he is going to deliver the lecture on the spectroscopy. And now I would like to invite our principal sir, beloved principal sir, to give the welcome note. సార్, నరేష్ సార్ అది కొద్దిగా మ్యూట్ చేయండి. వెల్కమ్ నోట్ రిగార్డింగ్ దిస్ FDP. Sir, principal sir.
Yeah, very good morning to all of you. I'm extremely happy that the Department of Science and Humanities of Quiz College of Engineering and Technology, and especially the Department of Chemistry, who came forward to organize this faculty development program on recent advances in applied chemistry. The role of chemistry in technology is very high, as I came to know from the recent studies. The investment towards innovations in the technology when compared to other technologies, the chemical processes and chemistry attracts more investments to come up with new materials and processes to be used in technology. Chemistry has its role in the advanced technological areas like nanotechnology, computing, transportation and automobiles, and aerospace as well. But we don't feel the importance of this chemistry. See, nowadays we are using lot of computing devices, handheld devices, mobiles, computers, wherein the touch screens, foldable screens nowadays coming up. All this is possible with the different materials that are the innovations of applied chemistry only. So I appreciate the Department of Chemistry for conducting this FDP on the advancements in the applied chemistry. I thank the resource persons for readily accepting our invitation and be a part of our FDP program, especially Dr. G.V.R. Sarma garu, Professor, GITAM University, who is the resource person today. And I appreciate the efforts put in by our coordinators, Vasubabu garu, Kiran Kumar, and I thank the management for readily approving all our proposals to conduct FDPs during this COVID-19 pandemic period. And last but not least, any program will be successful only with the participation. Simply conduction is not successful. So the participation is, as I came to know, good number of participants have registered for this particular program. So I appreciate the zeal and enthusiasm shown by the faculty to register for this, and I wish all the participants this 5-day program will help you in knowing the recent advancements in applied chemistry and improve yourselves in your academics. Thank you for giving me this opportunity.
Thank you, sir. Thank you for your valuable welcome note. And thank you for approving this kind of FDPs for BSNH and other departments. And now I would like to invite Professor Dr. G. Srinivas Rao garu, head of the department, to address the today's program.
Respected Principal Dr. Vengatrao garu and respected Professor Dr. G.V.S. Sarma garu and my colleague Dr. Vasubabu and the faculty of chemistry and the participants. Very good morning to one and all. A warm welcome to all of you and dear participants. Our college, IISc College of Engineering and Technology, was started in the year 1998 with a rural background, a backward district of Andhra Pradesh in Prakasam district, with an intake of only 180 seats. Now it is grown up to 1140 seats.
మీది రావట్లేదు సార్ మరి నాకు ఇక్కడ ఇప్పుడు వచ్చిన లిస్ట్ ఇప్పుడు ఇచ్చిన లింక్ సార్.
Sir, Kiran Kumar sir, please mute and.
The present intake of the institution is 1140. It is a very, now recently we got data science and artificial intelligence and computer science and business systems. This is the brief about our institution. Regarding to Science and Humanities department, we are very much strong in the surrounding areas of the district and also in the Andhra Pradesh. So once again, I am very much thankful to the management and the principal for permitting this conduction of FDP, and very much thankful to the particularly resource persons Sharma garu and Krishna garu, Nokaraj garu, and Dr. Venu garu and Dr. Ravichandran garu. Very much thankful to all of you, and I congratulate the faculty of chemistry to conducting this, and also very much good response from various states of India. Throughout India, more than 450 participants are participating in this. So I very much thanks to the management as principal and also to the participant, and very much thankful to the my resource persons of 5 resource persons of this, and also congratulate the Department of Chemistry. Thank you giving this opportunity.
Thank you, sir. And and we are planning a number of webinars in coming months also, and we are expecting same cooperation and financial assistance from the management and the Department of Basic Science and as well as principal, sir. And coming to the today's program, now the invited speaker is Sarma, sir. Thank you for accepting our kind request. Now the session is handed to today's coordinator, Mr. Prasad, Dr. Prasad, sir. Now he will intimate all the information regarding the Sarma, sir, and let the thank to the all the coordinators, principal, sir, and HOD and the management for being the here and as well as giving the welcome note. Thank you, sir. Thank you. Now, Prasad, sir, please introduce Sarma, sir. You read the profile of Sarma, sir. Prasad, sir.
Hello.
Yeah,
Hello,
you are audible. You are audible,
sir.
Yeah.
Okay, thank you, sir.
You please introduce today's speaker.
Okay, sir. Thank you, sir. Respected management, QIS College of Engineering and Technology, and respected principal, sir, P. Vengatrao Garu, QIS Set of College of Engineering and Technology, and HOD Basic Science and Humanities, Dr. G. Srinivasrao, sir, and today's distinguished facilitate speaker, Professor G.V.R. Sharma Garu, and participants and my colleagues. A very good and warm morning on behalf of Quiz College of Engineering and Technology. It is my pleasure and privilege to welcome you all to the 5-day national level faculty development program on recent advances in applied chemistry. It's my honor to introduce today's renowned speaker, Professor Ganavarapu Vera Raghava Sharma Garu, a person who is legendary in teaching service and research stream. He has 20 years of teaching experience and led many research projects successfully. He has completed his MSc from School of Chemistry, Andhra University, and PhD in the year of 1986, and PhD from IISc Bangalore, one of the premier institute in India, in 1993, and he has successfully completed 4 postdoctoral fellowship projects from University of Hyderabad, and University of Freiburg, Germany, and University of Chicago, USA, and University of Purdue and USA. Currently is working as a professor in GITAM University. He worked in different positions like Head of the Department, Associate Director, RC Research Chennai, Senior Science Fellow, Arjuni Research Bangalore, Senior Scientist, AVRA Research Hyderabad, and Research Scientist Landbaxi Research New Delhi. He has a great record under his eminent research guideship. Total 5 PhD scholars awarded under his supervision. Currently, 8 members of research scholars doing their research under his supervision. He has published 47 international journals in very reputed journals. He has received 14 patents for his extraordinary research during his career, and he bagged a lot of awards and rewards such like Inventor Award and Gold Medal for Best Research, Best Thesis from IISc Bangalore, and PG Distinction and Department of Chemistry, Andhra University, Best Student Award from Nagarjuna University, and many more uncountable. Ladies and gentlemen, we really get this kind of opportunity to listen to the words of great opportunity, great personality. So let us have the privilege of listening to the speaker. Sir, we are conveying heartfelt thanks for accepting our invitation and presenting your valuable time for your young generation. Thank you very much, sir. Now I would like to take over the session to our speaker, today's speaker, Professor Sarma, sir. Very good morning, sir. Sarma, sir, please take over the session. Sarma, sir. Hello, Sarma, sir. Hello, Sarma, sir.
ప్రసాద్ సార్
Sir.
ఒక్కసారి మీది క్లోజ్ చేశారు సార్.
ఓకే ఓకే సార్.
మీది క్లోజ్ చేస్తే ఇంకో కొత్త సెషన్ వచ్చేసి సార్, దాంట్లో నుంచి లాగిన్ అవుతాం అందరం. మీది అయిపోయిందా చెప్పడం?
అయిపోయింది సార్, కంప్లీట్ సార్.
ఓకే ఓకే సరే సార్, అయితే క్లోజ్ చేయండి సార్.
ఓకే ఓకే ఓకే.
College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547.
Vasbabu.
College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547.
జాయిన్ అయ్యారా సార్?
College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547.
Kiran sir.
సార్ ఆయన స్పీకర్ కి ఏదో సమ్ ప్రాబ్లం ఉన్నట్టుంది.
Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547.
Yeah. Good morning. Good morning. Very good morning.
Just a minute, sir. Sir, Naresh sir, live పెడతారా సార్ ఇప్పుడు ఇది?
Sir, just now completed introduction, sir.
Now, Kiran గారు PPT మీరు పెట్టేస్తే చాలు.
Rest of the participants, please mute yourself.
We request to all the participants, please mute yourself. Sorry for the interruption during the technical problem. Participants, technical problem.
Good morning, sir. Dr. Prasad garu, are you able to hear my voice?
Yes, sir. Yes, sir. Yes, sir. Carry on, sir.
Sir, Kiran sir. Sarma sir.
Just now completed. Sir, completed.
Yeah.
Just now completed, sir. Introduction of speaker.
Okay, that's why I was able to hear.
Please. Yes, sir. Yes, sir. Audible, sir.
Able to hear.
Yes, sir. Please hand over the session, sir.
Yeah. Now.
Please hand over the session, sir.
Now I have to access the PPT. I think Kiran Kumar garu has to. Okay. Either you can open from the first slide. The first slide. Before that, the first slide. Even before, one more. Yes. Very first slide. Yes. So I hope I can operate the slides. Or Kiran Kumaru garu, you can also operate the slides. I hope Kiran Kumaru is able to hear my voice.
Yes, sir.
Kiran Kumar garu, are you able to hear my voice?
Yes, sir. Yes, sir. Yes, sir. I am hearing, sir.
You can operate the PPT.
Yes, sir. I am operating, sir. So now you can check now, sir.
Hello. Yeah. I hope you can hear me.
Yes, sir.
Yeah. A very good morning to one and all. Particularly the organizers of this wonderful 5-day long national level faculty development program being organized by the Department of Chemistry, QIIS College of Engineering and Technology, and I thank all the organizers for choosing me as one of the resource persons for this 5-day faculty development program. The chief patron, Sri Nageshwara garu, president of the college, patron T. Venkatrao garu, principal, convener Dr. G. Srinivas garu, head of the department, basic sciences and humanities, coordinator for this program, Dr. A. Vasubhav Garu, Associate Professor, from whom I got the invitation. Thank you, sir. Organizers, C.H. Kiran Kumar Garu, Prasad Garu, and so on, and all the faculty members, and all the participants of this 5-day faculty development program. A very good morning to one and all. After so many topics that were given to me, I felt like choosing to talk a little bit about the spectroscopy. The spectroscopy topic itself is so huge. It's a course by itself. It runs into many volumes of textbooks. So, even to cover such a topic in a short span of time is really a challenge. And of all the spectroscopies, I have tried to choose NMR spectroscopy, okay, because of its significance. So before going further, I would like to thank Prasad Garu for giving me a wonderful introduction about me. I was able to hear from my laptop here. Okay. Very kind of you. But I am able to stand in front of you today is just because of the training that I was fortunate to have received from one of the great scientists, Professor Sri Krishna. Some of you might be knowing about him. He was an eminent synthetic organic chemist. He was working in the Indian Institute of Science, and he happened to be the first Ph.D. student of Professor Govardhan Mehta, another legendary scientist of this country in organic chemistry, passing out the University of Hyderabad as the first Ph.D. scholar. My professor, my guide, research guide, Professor Sri Krishna, after doing his postdoc and returning to India, he joined Institute of Science. And in those early years of first 2 to 3 years of his service at Institute of Science, it so happened that I was fortunate to get into the IISc, and he selected me to work under his guidance to get my PhD program, for which I am very. He was so excellent in analysis of NMR spectra, particularly. For that matter, all the spectra, all the spectroscopy techniques. And we used to get a lot of spectral data from various quarters of the country when I was doing my PhD. And he used to solve those, spectral problems and the structural elucidation so quickly in real time. What I mean by real time is that in a fraction of minutes or 1 hour, okay, he used to solve the structures, and we used to be there along with him. It's because of that exposure I am able to pull on the rest of my life. Unfortunately, he, because of a massive heart attack, he passed away in the year 2013. But he has trained a number of students like me, and who are occupying various important positions across the country and also across the globe. I'm very fortunate to have worked with him. With these few words, I will just move to the main topics that I am going to cover during this presentation. As I said before, spectroscopy is, as such, is a very vast subject. So, in that, NMR is one of them, one of the most important things of spectroscopy. That being a chemist, one should be aware of all the techniques, particularly the latest fundamentals of NMR spectroscopy. The more you learn, the better we become as a chemist. For example, take my own example. I started learning about spectroscopy in the year 1984, and today it is 2020. How many years? Around 36 years. Even today, I find the spectroscopy as a very new subject. It is so, interesting, and it is so useful in our walk of life, particularly field of science. In today's presentation, I would like to touch upon the various important salient features of NMR spectroscopy. For example, we try to understand the NMR spectroscopy by principle, and then we try to gain experience how to, how we get the data from the instrument. For example, acquisition, processing, and displaying of NMR data. And the third aspect is to gain experience in interpreting. It's not enough just we get the spectra, but how to analyze it, how to get useful information from the data. That is much more important. That is where our intellect stays. Okay. So instrument gives the data, but how to analyze the data in order to get useful information. And in today's context, we are going to talk about with respect to organic molecules, not necessarily organic molecules in general. It could be any chemical compound having magnetic nuclei. Okay, NMR data can be obtained, and that data has to be analyzed properly in order to get useful information. And the last topic, but the most important topic, is several techniques which are being developed. Still, it is in the process in the NMR spectroscopy in order to gain more and more use of this spectroscopy. These are the topics we will be going to cover. To begin with, what is spectroscopy? The study of the interaction of matter and electromagnetic radiation. We all know about matter. Matter is nothing but any chemical compound, or a matter is substance. So we don't have to talk much about it. Electromagnetic radiation, we have to learn about. We have to know about it. What is electromagnetic radiation? It is very often abbreviated as EMR, stands for electromagnetic radiation. It's a radiant energy that displays the properties of both the particles and waves. So, both particle and wave behavior it possesses. Of course, there are different types of electromagnetic waves that make up the whole electromagnetic radiation in the form of a spectrum. That is what is represented by EMS, electromagnetic spectrum. One portion of electromagnetic radiation we know very well is nothing but visible light. All of us experience the visible light. We can see it is so harmless, even if you are exposed to. Okay. Sorry. So, if you look at the electromagnetic spectrum, it is spread from one end with the low wavelength to the other end with high wavelength. What I mean to say is the low wavelength represents high energy, the high wavelength represents low energy. It is also clearly shown on this slide. Left side, low wavelength gamma rays, highly energetic particles like radioactive substances, which liberate high energy radiation, which is very toxic. A human being should not get exposed unnecessarily, unless otherwise it is required. Followed by X-rays. X-rays are useful to a great extent for the different applications. But even then, okay, we'll be, next slide gives you more information about it. And followed by X-rays is ultraviolet, which is not as harmful as X-rays and gamma rays, but still ultraviolet rays also, if one is exposed unnecessarily, they could harm the human being. And after ultraviolet, we come across visible light, which spans between 400 nanometers and 700 nanometers. Okay, and this region is quite safe for the human. Okay, even if we are exposed to this band of light, we are not going to get affected, or we are not going to get harmed. Okay, it is not toxic. And now, after visible light, we come across infrared, which is having further less energy. Okay, and this is having its own applications like IR spectroscopy, infrared heating, etc., etc. And then followed by radio waves, which are having much lesser energy, and they find a lot of applications in daily life like radar, television, radio, and now we are going to add NMR. Okay, so next slide shows you each one of them. What is their effect? How they are used? Gamma rays. Okay, they are emitted from the nuclei of radioactive substances, elements, and because of their high energy, they can damage biological systems, human system. So unnecessary exposure should be avoided. Whereas X-rays, okay, they are useful to some extent for certain applications, but excess exposure is harmful. Ultraviolet, as I told before, it can cause skin cancer if a person is unnecessarily exposed to more towards UV light. Okay. Then infrared, I hope you are all able to listen my voice.
Yes, sir. Yes, sir.
Yeah, okay. Fine.
Yes, sir.
Thank you very much.
Yes, sir. Yes, sir. Thank you, sir.
Yeah. Infrared radiation. Okay, visible light we know. Infrared radiation. Okay, it's much less energy, so therefore there's no problem. And then radio waves, which we are interested. Why? Because these are having less energy, and at the same time they have tremendous applications. One of them is, from our point of view, NMR spectroscopy. Of course, there are radio waves, television, all other things are there. But NMR, we are interested in today's topic. Okay. Now, when we are talking about NMR, from the last slide we have seen electromagnetic radiation spectrum, and now we get into the energy of each radiation, which is expressed in terms of E is equal to h nu, wherein h stands for Planck's constant, nu is the frequency, NMR frequency. Okay. Below that, what is the information that we are going to get NMR? Precisely, I have put it here, like observable. What are the observable facts? Peak position. We come across in NMR spectrum, peak position, peak splitting, peak intensity, peak shape. How is it going to help us to analyze the spectrum and thereby derive some useful information like structural elucidation? These things we are going to understand from the later part of the talk. Okay. Now, a brief introduction about NMR itself. It is not a very old subject like many other subjects. It's not a couple of 100 years old. It is rather new. Like in 1945 only, a great scientist like F. Bloch and E.M. Purcell, they have published for the first time a paper and a review in 1946. Okay, on NMR spectroscopy and its usefulness, okay, in science, for which they were awarded Nobel Prize in the year 1952. And once the physical aspects of those NMR instrument was set up by Bloch and Purcell, and the chemists have taken over, like R.R. Ernst, one of the great scientists of this century, last century for that matter, and he developed a number of techniques which are useful in the structural elucidation of chemical compounds, for which he was awarded Nobel Prize in the year 1990. Okay, and since the discovery of NMR 75 years ago, it has spread from the physics to start with to chemistry later years, later decades. And slowly in the 80s, it spread, okay, research and now made the diagnosis, okay, like for example, MRI, okay, magnetic resonance imaging, which is conveniently used in today's health systems. You see the development of over the days. And in order to understand better, or in order to create some interest in NMR spectroscopy to the delegates, I would like to put forward in front of you some of the most important applications of NMR. I have only listed very few of so many other applications. Okay, being a chemist, we are very much interested in the first part. The first topic is structural elucidation. That is nothing but chemical elucidation of a given chemical. It could be organic compound or an organometallic compound, any chemical which is having a magnetic nucleus. So we are very much interested to analyze natural products and their structural elucidation. Similarly, synthetic organic chemistry, it finds an extensive application in terms of characterizing the new substance. We do not know its character at all when we are first synthesizing. Okay, unless we have a proper NMR spectrum for such compound. Okay. Of course, NMR should be supported by other analytical tools such as UV, IR, mass, etc. Okay. Then only we can get the useful information. Yes. Yeah. Now continue. Typical applications of NMR. Another aspect is study of proteins and uh, polysaccharides, carbohydrates. For example, the protein structure. Okay, we can easily find out in today's context. Polysaccharides, carbohydrates, very complex structures. Okay, very difficult to what you call analyze. Otherwise, we can easily, not easily, we can analyze using NMR spectroscopy. Fourth application is metabolomics, means study of metabolites in a biological system, etc. etc. Fifth one is very, very important. Drug design. Drug design is a very, very important activity in our pharma industry, where the new drugs are developed based on certain principles. Okay, using, for example, structure-activity relationships, for which NMR is highly useful. Okay. Then similarly, in the area of health, medicine, magnetic resonance imaging is being extensively used nowadays. Okay, these are some of the applications. Okay, and the chronological development of the spectroscopy is shown here. 1937, Rabi, he is the one who first predicted nuclear magnetic resonance. Whereas in 1946, Bloch and Purcell have extensively studied, developed the instrument for which they were awarded Nobel, as I said before, 1952. 1953, NOE, nuclear overhoser effect. 1966, Ernst, okay, Fourier transform, NMR spectroscopy. So, for which he was awarded Nobel. Okay, Ernst, this Fourier transform NMR, I would like to talk a little bit about it. Okay, why? Because the NMR, when it was first developed, it was actually continuous wave NMR spectroscopy. Even when I was just joined for the PhD program, in the first year of my program, I used to use continuous wave NMR spectrum. Okay, it used to take a long time to record even one simple proton NMR of a given compound. Whereas after the invention of this Fourier transform NMR, the time required for recording NMR spectrum has tremendously reduced. Now one can record proton NMR spectrum of a given compound in 2 to 3 minutes. Okay, whereas otherwise it used to take hours. So that is the development. Like that, chronologically, some developments are given here. Everything is very important, by itself. 1987 3D NMR, 1990 pulse field gradients, and similarly in the next slide we have some more 2000 dynamic nuclear polarization DNP, and like that 2D techniques there's extensively developed in the last several years. Some of the prominent people who won Nobel Prize only based on NMR spectroscopy are given here. 1944 physics, Rabi himself got Nobel Prize. 52 Bloch got Nobel Prize in physics. 91 chemistry, Ernst got Nobel Prize. 2002 chemistry, okay, is Whitrich. Okay. He won the Nobel Prize particularly for protein structure identification, etc. 2003 medicine, okay, University of Illinois, Champaign, Professor, and University of Nottingham, Mansfield, they both share medicine Nobel Prize. So that itself indicates the importance of this area of research. Okay. Now you see, very interesting. When NMR was first invented or discovered, they have recorded the spectrum, NMR spectrum of water, simple water, and the spectrum obtained is shown on this slide. You see, can you get any information? Suppose if I were to be there, I would just simply discard this spectrum. Why? Because we cannot analyze anything from here. But from that point onwards, in today, we are able to get very sharp peaks in the NMR spectrum. Why so much? Even water itself, if you record today, it will show very sharp peak in the spectrum. So that means even little piece of information they were able to analyze and develop it further. And this was published in Physical Review 1946 by Bloch. Okay. That was the first experiment. Now, what is the basis of NMR experiment? Okay, let us come to it a little bit about the principle, to learn about the principle involved here. So, any nuclei, okay, this slide shows you a brief information about a given nuclei, provided it is magnetically active. Okay, it has got magnetic moment. When it is placed in external magnetic field, okay, there is going to be a moment, what we call magnetic moment, and that is expressed with the help of an equation, W is equal to gamma B0, wherein W is represented by frequency, okay, and gamma is the magneto-gyro ratio, B0 is the field strength. What is the field strength? It is expressed in Tesla. 1 Tesla is equal to 10,000 Gaussians. So now, what we understand is from this slide that any magnetically active nuclei first revolves around itself, and particularly when
College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 924641. College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547. Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547.
సిస్టమ్ యాక్సెస్ వచ్చింది కదండి. ఓకే, నేను వ్యూ చేస్తున్నాను. నా బోత్ ల్యాప్టాప్ నుంచి ఉంది ఇక్కడ మూమెంట్. ఒక్క నిమిషం, ల్యాప్టాప్ పర్వాలేదు. ఇక్కడ నేను నా సెల్ ఫోన్ లో కూడా స్లైడ్ కనపడుతున్నది. ఓకే
సార్ వాసు సార్
అంటే స్లైడ్ మూమెంట్ అనేది మీ అక్కడ. ఓకే నమస్కారం.
Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419530. Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact.
Yes, sir.
I will continue.
నరేష్ సార్ ఓకే కదా?
So, where we left it out, we come back to our topic. When we are talking about the magnetically active nuclei, the nuclei itself will be revolving around itself, and in addition, when an external magnetic field is applied, it will start rotating around the axis of the magnetic field, applied magnetic field. So there are two spins, and finally, what is the actually outcome? Outcome is generation of different energy levels. That is what is shown in the next slide. Two energy levels, plus half and minus half, and this separation of these two levels depends on the magnetoguidic ratio, which is represented by the equation that we have learned in the previous slide. And it is a characteristic property of a given element. If it is proton, it has its own value. Carbon, it has its own value. Okay. Depending on the element, this magnetoguidic ratio is going to be present. So here, what is the message that we have to take is that the larger the magnetic moment of the nucleus and the larger value of magnetoguidic ratio, the easier it is to see in NMR spectroscopy. That is what is important. Okay. Now, it is going to create a spin system, which is expressed in terms of Larmor frequency and represented by the equation W0 equal to gamma B0, wherein W0 difference frequency, gamma magnetic ratio, and B0 is the applied field strength. And precision is very important here. The circular movement of the magnetic moment in the presence of applied magnetic field. That is what is shown in this slide. Okay. I hope you can see the rotation of this arrow around the applied magnetic field axis. Okay. Then, in this process, there are several equations we come across. Physics person is more interested in learning about these equations, but from the chemistry point of view, it is worth removing these equations. Okay. W is equal to pi V, that is frequency. W0 is equal to photon, U is photon. W0 is equal to gamma B0. Okay. So from this, one can get the information of frequency and applied magnetic. Now, in this process, as I said before, different energy levels are going to get created. They are treated with quantum mechanical measurements, and an equation is derived, mu is equal to gamma A, where J is the spin angular momentum, okay, spin angular moment, which is going to get created, and eventually this leads to different energy levels for different types of magnetically active nuclei. Suppose, why I'm saying magnetically active, if an element is magnetically not active, it is of no use for us in the NMR spectroscopy. For example, carbon-12 they don't keep any NMRs that we all know. Why? Because they don't have magnetic moment. And what is the then condition for an element to show magnetic moment or spin? Is that if the atomic weight is odd, for example, C13, proton H1, then it will have spin that is representative of I is equal to half. So therefore, for proton 1H, C13, F19, and B31, spin represented by I is equal to half. Now, for certain nuclei, the atomic weight is even, atomic number is odd. For them, the spin is 1. There are other types of nuclei for which the atomic weight is odd, atomic number is also odd. If both are odd, their magnetic spin is equal to 3 by 2. So, there are total 4 types. Some elements don't have magnetic moment at all. Their I is equal to 0. Some are, others are magnetic active. And among them, there are 3 types. Those having the odd number of, the atomic weight is having half. And those having even number is 1. And for those nuclei in which both the atomic number and weight are odd, the spin is 3 by 2. Now, what is this spin number going to signify for us? When I is equal to half, when I is equal to half, when I is equal to half, go to the next slide, please. Oh, sir. Connection close to this one. There is some problem. Connection. Kiran Karu has to this one. Connection is close. Kiran Karu, can you?
Yes, sir. Yes.
Can you hear? Can you give access to any desk or PPT?
Can you try one more,
you can
sir?
also move that to the next slide, which I am able to see my. You can also operate there.
This one,
so you have
sir?
to move from the slide, spin quantum number to the next. Yes, next slide we have to go. The network has time to go there. Yes, connected. Yes. Now it is. We will accept it. Now, there we are. All right. So, from this slide, we are moving to the next slide, which represents the spin number for different types of nuclei. After learning about the types of nuclei, and the most important that we are interested in our normal course of studies in chemical research, we come across certain nuclei represented by H1, most dominant element in the chemical compounds, particularly organic compounds, followed by carbon, C13. Okay, carbon is present to a great extent in the compounds, and other elements such as nitrogen, chlorine, phosphorus, they are present sometimes, not, but still they are present in some compounds, and even if they are present in small quantities, their NMR studies can be performed. Why? Because N15, F19, P31, particularly P31 is so useful when we are studying the biological molecules. Okay, so we are more interested, or we are more going to revolve around proton and C13. Okay, now yes, this slide shows. This slide shows. I hope you are able to see. slide show. Yeah. So, different elements which are magnetic active and their abundance. Abundance is the important thing. For example, H1, its abundance is 99.98%. Okay, that is why we are able to record the NMR spectrum. Okay, NMR spectrum of chemical compounds containing protons. Okay, there are several effects. First of all, its spin is half, and that means there are only two energy levels created, which we will understand in the coming slides. At the same time, its abundance is also very high in the form. So these two aspects favor the study of chemical compounds using NMR spectroscopy, particularly with respect to proton. Okay. At best, when it comes to the C13, although its spin is half, which is equal to proton, but its abundance is 1.108%, which is very, very low. Okay. So that means we need a large quantity of chemical compound if you have to study the NMR spectrum of carbon. Okay. So that this slide shows you the energy levels created. When I is equal to half, two energy levels are going to get created. Yes. Okay. So when I is equal to 1, you see what happens? There is a rule called this is 2i plus 1 rule. That is 2 into 1, 2 plus 3. 3 levels are going to get created. Whereas here 2 into half plus 1, that is 1 plus 1, these 2 levels are getting created. So when I is equal to 3 by 2, can you guess how many states are going to get created? I is equal to 3 by 2. 2 into 3 by 2, okay, plus 1. That means 3 plus 1, 4 energy levels. So as the spin number increases, complexity is going to increase tremendously. That means, in other words, number of energy states are going to get created, because of which electron density is going to get varied in different energy levels, and therefore we are going to get more and more complex peaks in the NMR spectrum. So fortunately, it's happened in the case of proton. Only 2 energy levels are created, and that is why we are able to see a relatively less complex spectrum in the substance. Now, next slides. What is the significance? What is the energy gap between the two levels? You take, for example, proton having spin of half. It is going to create 2 different energy states. Okay, and there is an energy gap between these 2. Okay, because of this energy gap, not all the electrons are going to be present in the lower energy state. Why? Because the energy gap, although we are able to show the difference here, but in practice, the energy gap is so small that the population of the protons in 2 states will be almost equal as shown in the next slide. Okay, you can see this is one slide which gives you a formula to find out number of energy states depending on the type of nucleus. The formula is 2i plus 1. If you know I, that is spin number, I is equal to half. 2 into half plus 1. 2 energy states are going to get created. Now, in this slide, there are 2 diagrams given to you. One is expressed in terms of this gap between these 2. Okay, and this gap can be increased by the application of additional field strength. If you increase the field strength, the gap increases. That is precisely you are going to observe when you change 100 MHz NMR to 300 MHz NMR, 600 MHz NMR. That energy gap is going to get increased, and that is going to reflect, in the simplification of the spectral data, or spectrum by itself. This shows the energy levels, and this is what we have talked already. Now, very important aspect is Boltzmann distribution of states between different energy levels. Now, we all know the Avogadro number, right? 6.023 to 10 to the power 2 atoms in 1 mole of the substance. At a given point of time, considering protons present in a chemical substance, how do we calculate? We calculate number of protons as the Avogadro number, and that is a huge number. And according to Boltzmann distribution, since the energy gap between the two states is not high, so therefore all these protons need not see the lower energy state, although it is low, but do not enough gap in the higher energy level and lower energy level. Because of this reason, almost equal quantity of protons are going to be present in both levels. But at the same time, if both levels are occupied by equal number of protons, then it is not going to show proton NMR spectrum. Why? Because it is not going to show any magnetic moments. Okay, therefore we are not going to see any peaks in the NMR spectrum. That is also of use to us. On the other hand, although energy gap is less, okay, most of the the atoms are present in both states to a great extent. But there are still few molecules or few atoms which are going to be present in the lower energy state. Therefore, the density of the lower energy state is somewhat more than compared to the higher energy state. So therefore, how to know how many atoms are present in the lower energy state, how many are in the upper energy state, which is expressed by the Boltzmann distribution. The equation is n upper by n lower is equal to e power minus gamma capital H small h by kT, wherein n represents number of atoms present in the lower and upper states of the two energy levels. Gamma is the magnetoguide ratio, and H is the applied magnetic field, nothing but the B, okay, and the H is Planck's constant. K is the Boltzmann constant. Capital T is the absolute temperature. Now, we practically calculate in terms of the ratio of proton present in upper energy state, lower energy state, when like 1.4 Tesla of magnetic is applied on proton. Okay, and finally, what we get from this equation is that there is a gap of 62 atoms of hydrogen are in excess in the lower energy state than compared to the higher energy state. Although this number is not much, still this small number is good enough for us to create a difference in the concentration or density of the atoms in the low energy state, higher energy state. Or when we give some energy from outside in the form of radio frequency, what is going to happen is those which are going to be present in the lower energy state are going to go into the higher energy state. Okay, there is some. Yeah, going to the higher energy state because of force. Yeah, we have to go back to the screen. Kiran sir, I think we should go to the PPT. Yeah, I think we somewhere lost it.
Sir?
Yeah. Okay. You're back? Right.
సార్ మళ్ళీ వెళ్ళిపోయారంటున్నారు. అన్ని కరెక్ట్ గానే ఉన్నాయి, అన్ని బాగానే ఉన్నాయని చెప్తున్నాను సార్. ఏం చేయమంటారు నన్ను? ఏమో మరి.
Quiz College of Engineering and Technology, Ongole. The first
We're talking about de-shielding effect. Okay. Yes. Shielding is it's caused by other nuclei other than the nuclei which we are talking about. Yeah. So suppose we are talking about let us say proton. How the proton is surrounded by other nuclei. If you are talking about carbon, how even carbon is surrounded by other elements such as hydrogen, nitrogen, phosphorus, etc. So therefore this equation is also very important. B equal B into 1 minus sigma, which will decide the shielding and de-shielding effect of the given nuclei. Okay. Now this is a typical. Okay.
సార్ మళ్ళీ ఫోన్ వస్తే డిస్కనెక్ట్ అవుతుంది సార్.
అదే సార్ ప్రాబ్లం, ఫోన్ వస్తే డిస్కనెక్ట్ అయిపోతుంది.
Quiz College of Engineering and Technology, Ongole. The first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547.
Sir, Sarma sir, please unmute your microphone, sir.
Yes. Okay. So we are talking about the thermal spectrometer, which consists of three essential parts. The major part is superconducting element. It varies depending on the type of instrument they're talking about, 100 megahertz, 300, 400, 600. Nowadays, the 1000 is all, has become very common. Okay, that is represented by vertically placed cylindrical equipment. And then we have a box-like thing kept here, which is going to provide frequency. Okay, radio frequencies. Required radio frequency is required in order to excite the nuclei present in the substance. And there is a place at the top of this equipment you can insert the NMR sample. Okay, and very important is a chair. A wooden chair is very important. A computer monitor is there. This wooden chair is having a role. We cannot use any metal chairs here. So why? Because it's a magnet. So in this room, no other metal substance should be present. That's why a wooden chair is very important in NMR. Okay. So now we have a source of frequency, we have Superman, and we have a computer terminal in order to analyze the data. Okay, convert into the spectrum. That is what is after a printer. Okay, this is now once we get the spectrum of the instrument by doing appropriate Fourier transform calculations. Okay, then we get the spectrum in which the peaks are separated from one another. There is a complex, a number of peaks could be observed depending on the complexity of the molecule we are talking about. Okay, some of us are here, but for a question, this could be how do you find out chemical shift for a given proton or a given carbon is based on the equation delta is equal to n minus n reference into 10 power 6 by n reference. This n reference is nothing but the frequency of the instrument. If you are talking about a 300 megahertz instrument, the n reference is nothing but 300. If you are talking about 1000 megahertz instrument, n reference is 1000. That n is the actual frequency of the particular peak we are talking about. For example, methyl group, which comes at 3 delta here. So we are talking about its frequency. What is its frequency? So the frequency is going to be higher than the reference frequency. Why? Because the reference frequency is always kept at 0, which is nothing but that of the tetramethylsilane. Tetramethylsilane is standard we use both in proton NMR spectroscopy and C30 NMR spectroscopy. Why? Because it is having a high shielded protons or carbons. So therefore, it is taken as a sign. And there is another reason why we use tetramethylsilane as the standard is because if we don't use a standard, still we can get the peaks, but the position of the peaks will be different depending on the frequency of the instrument. If it is 300 megahertz instrument, our peak will go at some place. If it is 500 megahertz, it will come at different place. 1000 megahertz is still a different place. Then we cannot generalize where O-methyl comes or N-methyl comes. Okay, so for that purpose, in order to generalize, okay, what they have done is internal study is taken, like tetramethylsilane, whose shielding is high, therefore it is always coming at high shielding. That is given as 0 delta or 0 ppm. And with respect, all other peaks are assigned. And what is the advantage? Now, the methyl attached to oxygen, it is going to come always in the region of 3.5 to 4. Okay, irrespective of the magnet, 300 megahertz or 500 megahertz instrument or 1000 megahertz instrument. Okay, so even if you change, suppose here we are taking 11.7 Tesla instrument, you can increase it to 22, but still the position of the methyl is going to be same. Okay, for example, here it is 500 megahertz NMR instrument, for which a magnetic field strength is 11.7 Tesla. But if you go to 1000 megahertz, obviously this is going to increase 22, 23.4. At that time, without a standard, what happens? The position of the proton also will change. So in order to keep it at constant, okay, we use that as well. Okay, so whether you take 500 or 1000, the position of the peak is going to remain the same. this is be effective. That's what earlier I was trying to explain. Okay, we have applied some 11.7 Tesla on a given chemical substance, but the effective magnetic distance experienced by a given nuclear present in different environment is going to be different. That is why we are able to see different peaks in the mass spectrum. Okay, so that is a very important concept one has to get. So this is what the typical chemical proton in the mass spectrum of ethyl alcohol CH2 OH, okay, which is shown here, and this is compared, okay, with the first NMR that was recorded in the ethanol, okay, and you see the peak clarity, okay, during 1940s and 50s, okay. Now the latest NMR instrument with the clarity, okay. So you see the difference. But one should appreciate those scientists, even with that little bit of clarity, they were able to characterize so many complex organic compounds. Okay, but now we don't have to struggle so much, but still, okay, there much more challenge. Okay, in all here, if you take today's NMRs, let it be 200 megahertz or 500 megahertz, the peaks will be so clear. Okay, so this is what. So we'll be learning more about the splitting pattern and all that in the coming slides. Okay, why CH3, which is coming at the 1 delta. Typically, say, as I said before, TMS is the internal standard, and 1.2 methyl, usually aliphatic methyls come at 1.2 or so, and then D-methylene attached to oxygen will come around 3.5 to 4, and in this particular case, it is coming around this place 3.8 or so, and then the OH, okay, it is giving a peak here. Sometimes it may not give a peak, but definitely protons attached to carbon will show the peaks in the proton NMR. Okay. Now, this is what is shown in the next slides also. Right. Yeah. Now, just to understand, how the methyl groups, okay, will behave when they are attached to different hetero elements such as oxygen, silicon, carbon, etc. For example, O-methyl, just now we were talking about, will be coming around 3.7 as a singlet. Okay, and S-methyl attached to silicon coming at 0. That's why we are using tetramethyl as internal standard. C-methyl, okay, is going to come at 1. If a proton attached to carbon, which is having 3 chlorines, for example, chloroform, its peak will be appearing at 7.2 or so, 7.27 more precisely. Okay, so this is how it is. Now, with that, we try to apply this concept, right? In this slide, basically the information given here is usually the aliphatic protons, okay, they will be appearing near 1 delta, and tetramethyl is always 0, and some of the methyl groups will appear around 0.9 delta, and so by looking at this spectrum, we can easily conclude that this must be a hydrocarbon, like a petroleum ether. Okay, or since he is giving intensity also 6 hydrogens. Okay, that means 2 methyls are there, and here alkanes here he has not mentioned integrity. Okay, integration. So therefore, we don't know how many methyls are there. We have another example of this type. We'll be seeing that. So, what is meant by chemical equivalence and number of signals we are going to obtain, okay, based on the chemical equivalence. That we can calculate by taking 1 or 2 examples. Here, this for our own understanding, a small question. Okay, how many signals will the following compound show in their proton and the mass spectrum? The given hint is check for symmetry also, very important. Okay, so
sir. What happened?
Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530.
In this slide, we are talking about chemical equivalence, number of signals update. Small question for us exercise. How many signals will the following compound show in their proton mass spectrum? There is a hint also given. Check for symmetry. There are several examples. We are not going to work all those. Just practice question. Cyclopentane, for example. By looking at it, we can see it has symmetry. Okay, across the carbonyl group. So therefore, methylene group attached to inside will be coming as the one. Okay, that's my understanding. And then another methylene, which is just superimposable to the other methylene. So therefore, we are going to get, okay, let us say 2 signals in the NMR spectrum. Okay, that's how we can work with it. For example, those things one can work on. Okay, similarly, even O methyl here is going to give one. And the other one is symmetric, ethyl. So they will be giving only one set. Okay, we can take some examples in the later slides. Similarly, there is another question. How many signals should appear in the proton NMR spectrum for the Paul compounds? Okay, given is one side is 2 plus 5 carbons, the side also 5, 4 carbons. 4 means ethyl butyl ketone. Okay, but it is not symmetric. Okay, we can calculate how many. Similarly, octave is given, for which I think in the next slide, yes, there is an NMR spectrum of octave given here. Just we spoke about this, right? I spoke about the 6 hydrogens, which represent 2 methyls on either side, represented by A, whereas the methylenes in between are going to appear, okay, as a singlet. Then you can ask me a question. Okay, so what does it mean? How do you interpret it? This is where the term chemical equivalence coming into picture. These methylenes, although there is a difference, but because of their very close frequency, they are all coming at similar place. Yeah, of course, if they are having symmetry, they have to be called as chemical equivalent, and therefore they give you a singlet. Okay, that is what is observed in this case. Okay, so that is what we have to understand. This is nothing. There is a word given also, overlap of proton nerves. Okay. Although you see there is a representation BCD from here BCD. What does it mean? They are not equivalent. There is a difference among them, but because of their close frequencies, all of them are coming as a singlet. Okay, that is nothing but what we call overlapping. Okay. Similarly, another example. How many signals will the following compound show in their proton? Take the check for symmetry here also. For example, cyclohexane, highly symmetric. When you record the proton NMR spectrum of cyclohexane, it will give you as a star peak. Although it may not be sharp, little broad, but still one peak only will get. Okay, so like that. Okay. Now another thing that comes, we have studied it in earlier places also, right? Different Sahar's formula, Newman projection formula. Okay, so for a given molecule, if you can write the Sahar's or the Newman projection formula, how the protons are placed in the space. Okay, if they are trans, okay, they behave differently in a NMR spectrum. If they are cis, they behave differently. That means even that a small difference can create a difference in terms of the frequency. So therefore, they appear as different peaks in the NMR, proton NMR spectrum. Okay, this slide shows one example of tertiary-butyl. Okay, this is how many other neopentanol molecules. Okay, in which 3 methyls attached to carbon, they are identical. So therefore, what we call chemically equivalent. That is why they are going to show as a singlet at one. Okay. And whereas CH2 attached to oxygen, okay, is going to appear somewhere around 3.5 or so, 3.4. In this case, it is around 3.3. So, as a singlet, singlet only it is, because there is no coupling possible here. Singlet, which is a sharp peak which is appeared sharp at the peak. Okay, that is how one can interpret the NMR spectroscopy. Yeah, spectrum of a given compound. Okay. Okay. So, likewise, again, this next another aspect of studying NMR spectra is integration. Now, okay, once we have subjected our substance to collection of different frequencies by the NMR instrument, and we have subjected to Fourier transformation, and it has resulted in a spectrum which is printed on a paper, okay, in 2 dimensions, and then you see that peaks in different locations of the spectrum, and then, but how do you know that each peak represents how many protons? That is what is represented by integration. Okay, integration indicates the number of protons present in each are represented by that particular given peak in the NMR spectrum. Okay, so if you take standard example, the same example, neopentramol, what we see is here integration. Okay, 9 protons, 9 is to 2 is to 1, 9 is to 2 is to 1. So this integration ratio gives us really how many protons are going to be present. Okay, similarly, when you go to this, I think most of us are aware of it, but I'll go a little faster so that we was reset by the other computer. I think, I lost the connection again to the desk. Can you please it is from my side, it is not getting connected. Any desk not connected is the
Net problem, sir.
I think net problem. Oh, okay. But meanwhile, if you can move the slides from your side also. Oh, there also it is showing like that.
Okay, sir.
Yes, from my end, net problem is there. Net problem is there.
Yes, sir. Next slide, sir.
Okay, let me. This is. You need to. Next slide. If you meanwhile, you can move to the next slide. Right. RS, yes. So, similarly, another example of, where we have added chlorines here. Okay, so when you put chlorines, the frequency of the respective protons are going to change. Okay, this change is what we are, earlier talking about in terms of effective magnetic field. Okay, the frequency of the proton attached to carbon, which is in turn attached to chlorines, is going to come at a different. That means its frequency is going to be different. Okay, it's because of the change in the magnetic field. Okay, so therefore, the more information can be obtained from such studies. Next slide. Next slide.
You can operate now, sir.
You have to accept it. You have to accept it.
Yeah, I accepted, sir. You can.
Okay. Right. So once we get equal, right. Next, the splitting of signals. Why do we get doublets? Yes. Now I can operate. Yeah. Thank you. Now, yes. Thank you very much. Yeah. Okay. Thank you. Now I'll go fast a little bit here. So as we know that already, proton NMR spectrum. Okay. Always there is number of peaks obtained for the given proton, that is represented by splitting. That splitting depends on various factors. Okay, the factors it means particularly the most important factor is the neighboring protons, the immediate protons with which it is attached. Suppose, for example, peaks we have to get for CH3. That is what is given by this Pascal's triangle. Okay, for a triplet, there are 3 peaks in the ratio of 1:2:1, quadret 1:3:3:1, like the pentet 1:4:6:4:1. As the number increases, this number of peaks also going to increase by following n+1. It's a very simple, straightforward rule which is used, which is followed in the NMR, peak determination. Okay, so there are several cases here. For this only, like bromoethane, we get a quadret, we get a triplet. Okay, it's because of the protons which are attached to the neighboring. They are going to influence the peak splitting of the neighboring protons. Okay, so that is the this is basically this is very often we come across in NMR spectra doublet, like quadret, pentet, etc. Okay, so based on which we can this is going to give us information, right? Suppose if we find for an unknown compound a pentet, okay, that means we can immediately identify there is a presence of CH, for example, which is appearing as pentet, okay, because of the neighboring splitting, okay, neighboring interaction. Okay, the origin, that's what basically I was talking about. The origin of peak splitting is due to the presence of protons on the neighboring carbons, which will interact with the protons of interest, and then the number of peaks obtained will be decided by n+1 rule. Okay, so that is what essential. Okay, there is sometimes doublets and triplets. Okay, doublets. Okay, this is I can go fast. Okay, like that we can predict. Okay, the splitting pattern. In this example, for example, CH3 is going to appear as a doublet because the hydrogen attached to carbon having iron is going to split this the peaks of the CH3, peak of CH3. Therefore, we are going to get a doublet for CH3, whereas for CH proton, we are going to get quadret. Yes, it is right. We are going to get a 6+1, n+1 rule. Okay, so that is going to occur. That is so. This is exactly very complex. Okay, so this is what is the significance of this peak splitting in the NMR spectrum. We have to. So these are some of the commonly come across splitting patterns we observe in the most of the proton NMR spectra. Triplet, doublet, large singlet. That means broad singlet, large double-banded singlet, 2.1 very often. Multiplet 7, aromatic proton give multiplet around 12. Okay, the broad singlet. Okay, sometimes measure for OHR and NHR. Okay, so depending on the nature of this. Why I'm telling this one is whenever we observe such peaks in the NMR spectrum of our interest, we should think of that there is something of this protons present in our compound. So here is a slide which shows the way first data shows application of electroscopy with the spectral elucidation of natural products or drugs or drug-like molecules. One of the prominent examples is the Taxol shown on this slide. We can imagine this complex this molecule is, okay, and it was isolated from a bar, okay, in 2 days ago, and it is a well-known anti-cancer drug today called Taxol. Okay, it's some spectrum we showed here. Okay, now if you have to analyze this spectrum of Taxol and assign each peak to corresponding protons for this natural product, this Taxol, it is a picture. And P2 now is a like a methyl, where is methyl, where is OH coming, where is methyl, aldehyde methyl coming, where aromatic protons coming. By looking at this structure and the spectrum. But just image NMR spectrum, how difficult it is to, take from that stage. Okay, it is written here, to be able to go from this stage and to this stage. It is a big challenge, not that easy task. Okay. Next, similarly, sometimes we standard peaks obtained for certain types of compounds, like for example in this case, 2-phenyl-1,3 diarsine. There is the typical CH attached to two oxygens. Where does it come? Okay, aromatic regions. Where do they come? Typical peak pattern of this compound. Okay, it's just that we are represented here. We have to analyze by following all those rules. Okay, and then we can get the. So another area where NMR spectroscopy is extensively used is to study the reaction progress or a synthetic sequence progress. Okay, in a pharmaceutical industry or in an academic institute. Okay, suppose for example we are planning to synthesize a particular target molecule like the one represented here. Why we are going to synthesize? We are interested to synthesize such molecule, maybe for different reasons. It could be a pharmaceutical intermediate, or it is proposed by drug design people that this molecule is going to have a tremendous application. Maybe in today's context, maybe it can work as an anti-COVID or it can kill the virus. Suppose somebody has designed this molecule and asked us to synthesize. Okay, we are going to follow certain synthetic route for its synthesis. So in such case, how do you characterize the intermediates? Okay, that is where NMR spectrum is going to, or NMR spectroscopy is going to be very useful. For example, one of the intermediates data is given here. Its mass is given. Its proton NMR is given, and it's C13. It is given here. The proton is given here. Okay, so by following its proton NMR spectrum, mass spectrum, C13 spectrum, one can easily progress. One can easily elucidate the structure of the intermediate and the final compound. Okay, that is where the NMR spectroscopy is going to be very, very useful. This we talked briefly about earlier. Tetramethylserine is used as the internal standard. And now this slide is very important for us. That why we have to use sometimes 100 MHz instrument, why we have to use 300 MHz instrument, why we have to use 500, 600, 900 or 1000. Why should we use such a hi-fi instruments for the NMR spectrum recording? The reason is shown very clearly here. Suppose if I have recorded my compound using 500 MHz instrument, one of the protons is giving a doublet represented by this lower spectrum. Now the same compound, when it is subjected to 750 MHz NMR instrument, the same 2 peaks are going to be obtained and the same delta, but you see that they are well separated when compared to the 500 MHz NMR spectrum. Now go further when you record 300 MHz. Okay, the position of the peaks is going to remain same, whereas the peaks are well separated. Okay, so that means the separation quantity is also given. The separation of 2.7H, 5.6H, 8.5H. What does it indicate? That indicates it is going to further simplify our analysis part. That is why we are going consistently working towards the development of higher and higher NMR instruments. Okay. Of course, the cost of the instrument is going to also increase tremendously. For example, maybe 500 MHz NMR instrument will cost few crores, and 900 MHz instrument may cost around 8 crores also. Okay. So the cost of the instrument is also going to increase as the frequency increases. Okay. All these various spectra of different organic compounds, what people have done is they have made it to generalized rule that for a given organic compound, these type of protons will appear in this particular region between 0 and 15 delta as far as proton NMR is concerned. Okay. By the way, the range of proton NMR spectrum is between 0 and 15 delta. Okay. It is also expressed in terms of ppm. Okay. Aliphatic will appear at 1. Okay. Means what does it mean? Protons attached to aliphatic carbons. Suppose if the protons are attached to OH or ketone, then they appear around 2.5. Olefins around 5.3 or so. Aromatics always around 7.5, 7 to 8, etc. So, if any acid enhances presence is further down. Whereas the C13, the range of the spectrum is between 0 and 210 delta. Now, there is an interesting question here. We could ask, why is this difference? In the proton NMR spectrum, the range of peaks is between 0 and 10 delta or 15 delta. Yes, in the case of carbon, it is between 0 and 220 delta or 210 delta. So, now, in order to explain this, the easiest thing is, as I told before in the beginning, if you recall, the magnetostatic ratio of proton is different from carbon. And similarly, the number of electrons present in proton is 1, whereas the number of electrons, valence electrons present in carbon 4. Okay. And the surrounding environment of carbon is different from proton. So all these factors, cumulative effect, okay, will make the carbon nuclei to resonate at higher frequencies. That is why we see the difference in terms of the beta values. Okay. Now here also, after studying so many C13 spectra of different compounds, and a rule generalized that a generalized rule is passed. So it says that carbons present in the aliphatic region always appear between 0 and 50, and carbons connected to double bonds will be around 90 or so, and aromatics around 120, anywhere between 110 to 130 or so, and a carbon had, oxygen in the form of carbonate will be between 180 and 200. So this is how the equations of the carbons are fixed. Okay. So small variations depending on their environment is going to happen. Some of the readings, is the information provided here is obtained from these sources. Several textbooks are there. Some of the sources are there. Okay. Now spin-spin coupling also I told you before. We'll move forward a little quickly to see the NMR right. Okay. So now we are coming back to one of the old slides. That those nuclei having half spin are very much interested in terms of NMR spectroscopy. Why? Because they show peaks, of which we come across only proton 15 very often. N15 possible, F19 possible. You can convert to spectrum. P31 is possible. Okay, but they are less used in our studies. They are also used definitely, but they are less used in daily life. That is what it is. Now, I told before, in overall, if you look at the data involved in the recording of NMR spectra of a given compound, there are several stages: data acquisition, storage of data, and digital resolution. Okay, and then phase detection. All these are terminologies we across while we are going to convert the data into peaks. Okay, like for example, Fourier transformation, phase correction. Otherwise, if you don't apply all these techniques, we are going to end up with a spectrum which is not what it will not be looking good. Okay, when you can say you might be there are a lot of NMR studies. I have seen the peaks so typically appearing. Okay, but before that, there is so much involved that the operator does all these things, right, in order to make the spectrum appear beautiful. So they do a lot of actions. Okay, a typical frequency when it is applied also is shown here. Okay, in FID, okay, how it works. Okay, that is FID means pre-induction decay. So what they accumulate all the frequencies. Okay, then we record the spectrum of a given compound. first, all the frequencies are applied at first, and all the protons present in different environments are excited to the higher state, and they'll be coming back to the original state after releasing this frequency. And they give a bunch of frequencies output, and that output is subject to Fourier transformation, and they are split into different peaks at different frequencies, different phases in the spectrum. Triplet here, singlet here, quadruplet here. They are split into this. That is what we are seeing, only the final spectrum for analysis purpose. Okay, so this is what is essentially. If it is a single frequency, you get a single peak. Multiple frequencies, you get multiple peaks. That is what is essentially happening here. Let it be proton or C30 nanomole. Okay, we are going to end up with the different peaks. What we are concerned in proton NMR is about chemical equivalence, stereochemical equivalence or non-equivalent. Chemical shift is one important thing. Spin split, spin coupling, integration of the peaks. These are the important aspects which one has to remember when we have a study. There are several other interesting, topics also in the proton NMR spectroscopy, such as homotopic protons, okay, enantiotropic protons, diastereotropic protons. Okay, given compound, although you don't see anything directly, although you see, we say a molecule is chiral if at least one carbon is attached to 4 different groups. Okay, we say chiral. But without being chiral, also sometimes some protons behave as if they are chiral. They are called enantiotropic. Okay, some don't behave. They are called homotropic. Okay, so in this case, some of the examples of homotropic groups are one or two examples we'll see, and we'll move to the next one. Okay, 1, 2 details if you study, there is a plane of symmetry, and we think that it is symmetric. Okay, then such compounds are called as homotropic. And you take the other example, wherein CH3 attached to CHOH. Here there are 3 protons, and they can rotate among themselves, and then they can be called as homotropic. And here is a question, and there is a example given: 1, 2 dimethyl cyclohexane, but they are trans to each other. Methyl groups are opposite. One is beta, one is alpha, as you can see here. And with respect to these 2 protons, one is represented by red, other is represented by blue. And now the question is, the molecule shown below has C2 axis of symmetry. We know C2 symmetry is exactly first the top half here, mirror image of the bottom half. Now, so are the 2 hydrogens shown homotropic. Is a question. The answer is no, they are not. Okay, why? Because these 2 protons, which I are talking about, they are behaving differently. Yeah. So these molecules are distinguishable, and this is called a C2 axis. But in this case, okay. Whereas here, in the previous example, yes, the red H, blue H are not homotropic to each other. Why? Because this one is beta, one is alpha methyl. Because of this, they are not similar. That's at least. Okay. Now, cis methyls, there is no problem. Okay. Here, this is okay. These molecules are distinguishable, and this is what a C2 axis. Yeah. Okay. But the protons are going to be, they are not homotropic. They are not the homotropic. Okay. Enantiotropic, I told you before. Okay. Enantiotropic means you see when you are talking with respect to letter A, these 2 protons. Okay. Although it is not enantiomer, it is not a chiral compound, but they show that behavior. Okay. Such protons are called enantiotropic. Okay, this is another important thing. We often we don't pay much attention. Okay, here also the same question: enantiotropic or not? Okay, go to find out. We apply symmetry, and find out given proton whether it is enantiotropic or not. Similarly, diastereotropic. When do we come across this one? Already there is one chiral center present in a given compound. In addition, we are going to add another CH2, and those two protons, whether they are going to behave differently or similarly. That is what is represented by diastereotropic. In this case, they are going to behave diastereotropic, like diastereotropic protons. Why? Because if you write down the three-dimensional structures, these two protons behave differently with respect to each other. That is why they are called as diastereotropic. This can be better understood, I think, in the coming slide. This is very important, very interesting example, which explains how diastereotropic protons can be differentiated. Now you take this example in which C6H5 is attached to CH, COH, CH3, and CH2OH. That means it is C6H5, COH, CH3, and CH2OH. Now these two protons, this alpha and beta protons, they are diastereotropic in nature, and therefore they behave differently and give a splitting in the peaks. That is what is observed here. That is why I have shown this slide here. So they are called diastereotropic. Okay, this is one of the important. Many people don't pay attention, but while analyzing the spectrum, these things we have to do. In addition, in the proton NMR spectrum studies, we also use some techniques such as decoupling, spin decoupling. Suppose if you feel that your NMR spectrum is very complex, having too many peaks, you want to simplify, you can do spin decoupling, which will simplify the spectrum. Unnecessary couplings will be removed, so you can analyze better. Higher speed NMR spectra is another choice. It is what we were trying to learn about 500 megahertz, 50 megahertz, 800 megahertz instrument. By the help of such instrument also, one can separate the different frequencies in proton NMR spectrum. The same thing you will do, C13 also. Anthrite shift reagents are added, the peaks are separated in the spectrum. This is also one of them. So with that, we close the proton NMR and quickly pass on to the proton NMR. C13 NMR. The principles are very similar as that of proton, except here the nuclei is going to be different. Carbon, its abundance is also less, and its complexity is also high. That's why it is going to resonate at higher frequencies. As far as calculation of chemical shifts is concerned, it is same as NMR, proton NMR. And there are new techniques which are applied in imaging spectroscopy. Therefore, there's APT, attached proton test. There is another one, Dept, distortionless enhancement by radiation. These two techniques are extensively used in the carbon-13 NMR spectroscopy. Now, if you take a normal C13 NMR, you get a number of carbon peaks with the splittings by the respective hydrogens attached to it. A CH is going to show carbon peak split into doublet. CH2 carbon is going to appear as triplet. CH3 carbon is going to appear as a quadruplet. So that's why carbon and spectrum is going to become very complex. In order to simplify, what they did is develop new techniques called APT and DPT, which will, show, first of all, they record the decoupled spectrum, carbon, which all couplings with respect to hydrogens is removed, so that you get only carbon signals. Afterwards, they apply APT and DEPT, which will further give more information. We can see using one or two examples. This is the page I was talking about, internal standard TMS. And other things similar to Prof. Here, by using several a general tool, a carbon present in different environments will appear in different frequencies in the C13 spectrum. Simple aliphatic methods are are observed at around 20, CH2 around 40, PHX around 60, a carbon attached to just oxygen somewhere between 85, 90 and down 50, and C triple bond C carbons around 90, 100, 80 to 100. Olefin carbons 120, 140, aromatic carbons 150 to 140, C triple bond 120 to 140, C triple bond O around 180 to 200. Okay, this is what is generalized. Okay, this is a typical C30 spectrum decoupled of this particular example. Now the peaks are well separated. And, all of them are appearing as singlets. Why? Because peak of peak is taking place. And the number of signals also 1, 2, 3, 4. So we can say 5 types of carbons are present in this period. And CDCl3, chloroform, there's CDCl3 carbon appears around E. Okay, so this is how it is. Typically, the DEPT experiment is carried over by using 2 different frequencies, pulses. DEPT 90, DEPT 135 pulse. Okay, when you apply DEPT 90 pulse, only CH cells appear. Okay, in the spectrum. When you apply 135 pulse, CH3 and CH give positive signals. That means, both the baseline and CH2 give negative signals, that is below the baseline. We can see one of the examples how it is going to appear. This is a typical proton NMR, uncoupled. Okay, top spectrum. That's what is shown here, coupled. Okay, quadruplet, triplet, etc., doublet. But we don't like that. We want to simplify the decoupled spectrum, 2-bit form. Okay, and then when go for this DEPT and all that, right? DEPT 90 pulse and DEPT 135 pulse. If you carefully observe, when we use 135 pulse in DEPT, all CH protons appear above the baseline. Similarly, all CH protons appear above the baseline. There is no quaternary carbon. So we have that means we have removed the quaternary carbon. Okay, so the peaks will be simplified. Whereas CH2 carbon appear with respect to the Ph.D. Now, with this, we can use data to analyze C30 spectrum of a given compound. This is the typical DEPT spectrum of this one, where, as we told before, this CH and CH3 appear above the baseline, where CH2 appear below the baseline. So, what is the advantage? One could ask this question. Is analysis becomes simpler. That's all. We can, and not only that, connectivity of carbons can be easily identified. Now you know how many CH2s are there. There are 3 peaks down below the baseline. It indicates clearly the presence of CH2. The number of the peaks clearly states that there are 3 CH2s present in the compound. Okay. Now similarly above. So depending on the number of peaks, we can identify whether it is CH or CH3. If it is simple CH3, it will be around 20. We can easily see defective. If it is CH, it appears and moreover, if it is chromatic, it is going to appear at 120. Therefore, we say it is aromatic. So, lot of information that we have taken by this DEPT spectrum. Whereas APT, I told before, attached to proton test, which gives information about all the types of carbons, including quaternary. Okay, so right in the DEPT, quaternary does not show. That is what is observed here. Below, for example, here is going to appear as here, as here below the line. So that means APT gives information and DEPT gives better information. Likewise, we can predict NMR spectra of different samples. Okay, here the same set of rules are applicable, like symmetry. Okay, if a molecule is symmetric, we can say, okay, we can say that it's having C2 plane of symmetry. Therefore, the number of carbon signals obtained will be 4 in the case of methyl cyclopentane. Okay, right? So, like that. So, this quickly plays a major role in the identification of number of peaks going to be obtained. Okay, this is one type of. Similarly, the reaction kinetics we were talking about, application of reaction product study, all these things can be done by using C13 also. For example, a simple elimination reaction we are studying, and there are different products possible in the reaction, and 2 different products will give 2 different C13 spectra. From that, we can identify which product is predominantly formed in the reaction. Using that, one can easily distinguish between the products and therefore the mechanism of the reaction. Okay, so that is how the the reactions, progress of reactions, kinetics of the reactions, this spectroscopy can be used. Okay, like that we can go on doing several examples. Okay, right. Okay, a typical C13 of stone is having 3 peaks. 1 peak is due to the solvent CdCl8, whereas other 2 peaks are due to the methyls, methyl and the carbonate. The methyl carbon, aliphatic methyl coming at around 30, okay, and the CO carbon coming at around 210, okay, and the solvent also shows the peak. So this is how, and lot of data, lot of information is given on the right side, which one should not neglect. There's a lot of information is present, like the frequency of the instrument, the amount of the magnetic field applied, number of scans performed on a particular substance, like that. They are all given on the right side of the spectrum. Okay. Besides, C13 provides information about equivalent carbons, non-equivalent carbons, etc. Okay. So, like that, we can predict the products form. Just now I told the prediction of the products, the reaction can be obtained by C13. That is C13 NMR spectroscopy. We enter into 2D NMR. Okay, 2D NMR is the most important thing which all of us should be interested in. Right. So, as the research is progressing in NMR, more and more new techniques are coming up in order to acquire more data. Okay, take example, suppose you cannot get the useful information, or the information that we have to obtain from proton and C13 is not enough to assign a structure to a given chemical substance. We need more studies to be done. That is possible definitely with NMR itself by applying 2D techniques such as OC, correlated spectroscopy, where multiple frequencies, multiple pulses are given and the data is equated in 2 dimensions. Okay, 1 dimension, in particularly in the case of OC, 2 dimensions, both dimensions proton NMR is recorded, and finally number of frequencies are collected and they are represented with the help of the computer, and the output shows emergence of new peaks at certain locations. They are called cross peaks and diagonal peaks, and when the diagonal peaks are connected to one another, it will form the actual spectrum. Whereas the diagonal peak, cross peaks, they can be connected. Certain peaks present in the diagonal region, so that it is going to give information about which proton is attached to which proton in the compound, and then from there we can write the structure of the compound. So similarly, NOSI is the nuclear overall effector, okay, 2-dimensional. TOCSI, total correlated spectroscopy. Particularly, it gives information about protons of a spin system. Okay, all protons of a spin system. And then further refined is ROSI, rotating frame overhaul effector. That is, okay. HETCOR, heteronuclear correlation. That means 1 dimension you record proton NMR. other dimension you record C13, try to join them, you get cross peaks, and those cross peaks are going to give more information. Okay, this is a typical COSY spectrum of you see ethyl vinyl ether. Okay, so from this to these peaks, we can draw the two-dimensional spectrum. Okay, each axis is showing proton and NMR spectrum, and there are some cross peaks. When you connect these cross peaks, and what you want to know is the connectivity between these two protons. This proton and this proton are interconnected. Okay. Now, for our convenience, ethyl vinyl ether, the different sets of protons are already marked as A, B, C, D, E, and in the spectrum also they are marked here. Okay, and which proton, whether A proton is coupling with the B, or A proton is coupling with B, or E proton is coupling with C, such information we can easily obtain from the COSY spectrum. For example, A connects with B. From this, it is evident. It is evident that A protons are interact with B protons. Okay, drawing these triangles. Okay, so that means we can for sure tell that A protons are coupling with the B protons. Okay, that is how we can identify the coupling patterns. From that, we get more information than we got from the earlier spectrum. Similarly, you go for next, like that we can work out H core also. Now, what's the difference between COSY and H core? COSY is both dimensions proton and NMR is recorded. In the H core, one dimension C13 is recorded, other dimension simple proton and NMR is recorded, and then cross peaks are represented, so that we can identify which carbon is attached to which proton type. Okay, so H core is a more developed feature. Okay, so similarly, an OE effect also can be observed. So here, okay, here also 2D nosy spectrum. You see how 2D, okay, how it is going to look like. That means even fine coupling, nuclear overall effector means spatial coupling is also measured here. That means even small coupling also can be identified using 2D nosy spectrum. Okay, so that means more information can be obtained in the structural elucidation of the given unknown chemical substance. Okay, now you go to more better techniques. HMQC stands for heteronuclear multiple quantum coherence. The significance of this particular technique is that C13 is displayed in one dimension, proton spectrum is displayed in another dimension, like H core, but in addition to COSY, H core, in the case of HMQC, you get information about 3-bond coupling. That means a proton, its example is given HCCH. Okay, whereas HMQC shows 1-bond coupling CH. That means accuracy is going to get increased. Okay, so where HMBC, heteronuclear multiple bond coherence, the spectrum looks very much like HMQC spectrum in the case of HMBC also, except it shows 2-bond, 3-bond, or sometimes even 4-bond coupling. Okay, so even 4-bond coupling, what does it mean? Even if a carbon is away with another carbon, it's about 3 carbons away, how it is interacting can be understood by studying the HMBC spectrum. These techniques are used for very complex natural products or protein molecules or carbohydrates or those molecules which are more complex, okay, which cannot be analyzed by using protein, proton or C13 spectrum. Okay, so okay, in this slide I have shown one molecule here. This is a molecule which is synthesized by one of my Ph.D. scholars. Her name is Devi. Wonderful work, which I like very much. Okay, and you can see the complexity of this product. Okay, and now imagine it looks like a natural product, but it is not. it is synthesized very much in the laboratory, in our laboratory at GITAM University. Okay, and normally some of you are, maybe specialized in synthesis. You can imagine if you have to synthesize this molecule by using routine synthetic methods, how much time it will take, how many reagents it requires, how much effort it requires, how long does it take. Okay, it's a huge. But this molecule was synthesized in 2 to 3 steps. Okay, in just 3 to 4 days time. Okay, this molecule was part of the thesis of Devi. Okay. And she got a PhD in 2 years, 7 months. Okay, for this, a good piece of work which she has. Okay, so this for the studying, for the analysis of this compound, we have used all the whatever explained earlier. We have used all those techniques in our talk, or at least most of them. Protons, Ph.D for sure, clearly, OC. Okay, apart from mass, IR. Okay, we have used those techniques. Okay, so this is what I wanted to tell about the 2D techniques. 2D techniques are very, very important. So far we have completed proton, C30, and 2-dimensional techniques. Now we move to the most recent advancement as far as NMR spectroscopy is concerned. Okay, that is what we call MRI, magnetic resonance imaging. Now, this technique is extensively applied today in all modern hospitals, okay, where the patient is subjected to MRI and his brain is with the radio frequency, okay, and it gives a number of images, right? A number of images. In the first slide I showed you, okay, cross section of a human brain, okay, and in that, as you know, that the brain consists of a lot of water molecules, apart from so many other biomolecules. And this technique utilizes proton present in the water molecules present in the brain and taking MRI in different dimensions, different angles, okay, and accumulate all the data and finally analyze the data, cross-section of the data with that of the standard, with that of the standard brain, and they get useful information, okay, like identification of tumors, identification of some solid substances, infiltration of the brain, etc., etc. They can get such information be obtained by using the MRI. Okay, and at the same time, it is not harmful to the human brain or human itself. Or herself. That means the radio frequency after all we are using, which is not going to affect our human system. So that is why this is going to become very, very important in the coming days. Okay, the field of medical research. So with that, I try to come to the end of the my lecture. So just to summarize, that we have learned so far is what we have tried to learn rather is first point, we have tried to gain better understanding of NMR spectroscopy. We have already, probably most of us have studied NMR spectroscopy in different perspectives. Now today what we have tried to refresh ourselves, okay, where we stand today, okay, and how we have to look at NMR spectroscopy. Okay, our perception of NMR spectroscopy should change. That is what we have tried to understand. Second aspect is we are never bothered about how the NMR spectrum is obtained. All that we need is NMR spectrum for ourselves. But we need to understand the physics behind the working of the instrument, acquisition of data, processing of the data, displaying of the data in a meaningful fashion on the screen of the computer. That is all we should be aware. Being a chemist particularly, I am very much of the opinion that we should have a thorough knowledge of what is going on behind the screen, particularly as far as recording of NMR spectrum is concerned. Then only we can appreciate the data, how we get. Just analyzing the spectrum using standard rules, okay, in my opinion, is not enough. You can appreciate only when we can thoroughly understand the basic principle, what's happening behind, instrument, and then study the analysis of the spectrum. That will be interesting, also challenging. Third point is to gain experience in interpreting the NMR data. Okay, for known molecule, if I give peaks, we can easily assign peaks. Methyl comes here, methylene comes here, CH comes here, olefin comes here, aromatic comes here. Okay, that's okay. Yes, that is at the level of MSc or to just pass an exam. But our objective is not just to pass an exam. Actually, we have to apply in the real life, because I am sure the participants are, delegates who are already working somewhere as faculty members, teaching students in turn. So I think for ourselves, we should be, satisfied ourselves that, oh, yes, we are strong in this. Okay, we should appreciate ourselves what is the importance behind this. Okay, then only we can convey the message to others. Okay, the last one is we have tried to understand most recent advancements in the field of spectroscopy, NMR spectroscopy, one-dimensional, two-dimensional techniques. Like, for example, OC, ROSI, TOXI, okay, HEADCOR, okay. Similarly, your NOSI, 2D NOSI, and then you have HFQC, HFBC, okay. To be very frank, to be very honest in front of you, all I am telling, I am using those words so freely. But you ask me strictly, every time I get a doubt, what is HFBC, what is HFBC? Okay, I am telling openly, unless we practice this and use this for the analysis of some of our compounds, we don't become acquainted with these techniques. Okay, so that is why one should be doing research also. One should continue to do research. Although all of us are doctorates, if I will, most of our delegates are doctorates also here present, some of them at least. So although we got doctorate, but we should not stop our research at that point. We should continue in order to pass on this valuable information to the younger generation. That's my observation and feeling. And this slide shows my research group left those scholars who have already obtained their PhDs under my guidance. Maybe just whose molecule I just projected just now. Appal Naidu did wonderful work. Alice Robert, Appal Naidu is working in pharma industry, now recently got promoted after getting his doctorate. Dr. Alex Robert, she is a colleague of mine, working in GITAM University-Visakhapatnam, and she got doctorate with the guidance. Dr. VLN Sargar is working in the pharma industry. He got elevated with doctorate. Dr. Ananda Mohan is working as faculty, head of faculty in Ambedkar University-Visakhapatnam. He is also happy after getting doctorate. And right side, B. Madhavi currently working as full-time scholar of my guidance. Praveen, Pani Kumar, they are part-time scholars working in industry, but they are very good chemists. They are doing good. Sri Someshwari, one of the most senior, I'm what you call, I'm a little bit ashamed of saying Someshwari has started his work for my guidance long back. P.H.D. are there also. They're more elder than me, but their interest is phenomenal. They are still doing some work. And Somesh Reddy is a faculty by himself in a college, government college. And K.R.K. Prasad Garu, he is his own interest in Madras, Chennai. Is a little good turnout. Okay. But he is very much interested in this. Okay. So this is about my research group. I'm thankful to them because for their good contribution. And then, next slide. Okay, it is stuck here. It is stuck, not moving. Can we go to the next? Oh, yeah. So I think Karendara is already got to the next slides. Okay. So a brief mention about GITAM and Dept University. Glimpses of GITAM University. GITAM University is a university which is started from scratch by our founder president Sri M.M.S. He has dedicated himself to the upliftment, to the development of this university from a small college to the level of autonomous college and then deemed to the university, and in one place in Visakhapatnam, and he has made it to spread to different locations, Telangana, Andhra Pradesh and Karnataka. We have a campus in Banglore, we have a campus in Hyderabad, okay, and it is present in a beautiful location, and all the three locations are beautiful, particularly Visakhapatnam. Okay, Visakhapatnam is a greenery campus. I welcome all of you. I welcome you to visit sometime whenever you come to Wales. So make it a point to visit GITAM, to attend a conference or a personal visit. Fine. Okay, I welcome, and it is working there. Yes, maintained very much. Okay, in order. Okay, and this slide shows GITAM Hyderabad, Bangalore campuses. GITAM Hyderabad campus is beautiful. Why? Because it is such a huge building, in hundreds of acres. In one location, one building, all the branches are present, all the institutes are present. Name it: Science Institute, Engineering Institute, your Pharmacy Institute. Okay, any institute, all are present in the same building. The building size is to visit, then only there is. Okay, I myself could visit only last year. Okay, after so many years. Okay, I was thrilled by looking at that. Bangalore campus itself is again this huge campus. Okay, having all the branches like we have. Next one, next slide, please. Can I next slide? Yeah. So this slide shows the medical college, which is an operation present in Visakhapatnam. It's a wonderful, you will be thrilled to visit the building. Okay, it's such a huge building, infrastructure, very fit to medical college. Unfortunately today, a lot of COVID patients. It is given to COVID patients in wider risk. GITAM Medical College is chosen for keeping the COVID coronavirus patients. They are being treated as okay, and we have, apart from this, we have so many other colleges like GITAM Institute of Law, Dental College. We have then we have Pharmacy College, Pharmacy Institute. Okay, in Institute of Social Sciences. Like that, every branch, like any normal university has. Okay, and Sri Murthy has built the infrastructure in such a wonderful way, and his built the structure and shaped by his sheer efforts. Okay, and which is present in such huge locations, covering hundreds of acres. Okay, and all three campuses put together, we have about 1,500 faculty and several thousands of teachers also. All put together, thousands of employees working. So this is all about the university. And this year, our NIRF ranking also is improved quite a bit and compared to last year. We have jumped about 14-15 places ahead. Okay, then compared to many institutes which are lagging behind. Okay. Still, it is not very high. It is still the number is high. That means we have to put a lot more effort in order to make it much more stronger. And we have hundreds of research scholars work. We have in Science College, we have MSc programs, integrated MSc. We have 2-year MSc program here. We have BSc normal program, BSc honors program we have, and we have, apart from that, we cater to the need of the engineering. BTech we have chemistry, as we know, we are your college and our college. We teach engineering chemistry. We until recently we were teaching environmental studies as one of the subjects. I myself teach, apart from these subjects, German also as one of the subjects as a foreign language for B.Tech, or that is as open elective in the 4th semester. So, like that, we have these things. So, this all about from my side. Next slide, please. Kiran, next slide. Yeah. So with that, next slide, last slide we come to. Thank you. Thank you, slide. Thank you all for your kind attention. Okay, and thank the organizers once again for choosing me as a resource person. Okay, for this 5-day national faculty development program on recent advances in applied chemistry, which is very relevant in today's context. Learning chemistry is different. Applied chemistry is much more different. So what we need in our country today is application of science. That is very important. That is lacking of application. Already we are experiencing in this difficult time of COVID-19. Okay, lacking not having enough PPEs or medication, or for that matter, all over the world experiencing same thing. But at the same time, after realizing that we are the first one to develop better, manufacturing of drugs. The entire world is dependent on our countries, and particularly pharma industry. Okay, our manufacturing of drugs or vaccines, okay, is going to be crucial for the entire world, and for which we chemists are required very much. Why? Because pharma drugs analysis by spectroscopy, particularly NMR, is very essential. Okay. Having knowledge in this area, I'm sure, will add a feather, okay, on everybody's role. Okay. So with this thing, I would like to thank once again the President, Convener, Principal Sir, Head of the Department Sir, and the Coordinator Sir, and Prasad Sir, Vasbabu Sir, Sino Sir, Chori, Venkata, Principal, President, for giving me opportunity to present them. Okay. What I know about this area of research. Thank you all. Thank you very much. Prasad Garu? Prasad Garu.
Thank you very much, sir.
Thank you.
Sir, we have some doubts from participant side, sir.
Yeah.
So please,
Yeah.
Kiran sir, please tell me the doubts. Kiran sir?
Sir?
Yes, please. Yes, please.
You can speak, sir.
Yes, yes. I can. I'm able to listen.
Kiran
In
sir,
fact,
please ask doubts.
I am supposed to.
No, sir, you can conclude, sir.
Okay, sir.
Okay. Actually, I was supposed to join another meeting, which is being conducted by our Department of Science and Technology, Ministry of Science and Technology today. That is another like our webinar. Okay, they are also conducting a webinar about how to write projects and all that. Okay, so that will be. I think I will be joining after completing this. Okay. So okay. Anyway, I hope I am trying to convey some useful information to all the colleagues. Okay, and if any shortcomings are there, please your feedback is very essential to me. Any area where I can add more information, if you can send me in terms of a mail or so, I can improve. Sometime in future, certainly we will. We can have a better presentation. Thank you. With that, thank you very much. Once again.
Thank you very much, sir.
Yeah.
Thank you very much, sir.
Thank you.
So
Okay.
once again, we are conveying, sir, my heartfelt thanks to you, sir.
Okay.
Thank you very much, sir, for spending your valuable time, sir.
Thank you, sir.
Thank you very much, sir. So now participants, please your IDs. Now from today's session. Thank you.
Quiz College of Engineering and Technology, Ongole, the first autonomous engineering college in Prakasam district, AP. For admissions, contact 9246419530, 9246419547.